So the last set of things, the objectives that we're going to look at today is we're going to look at these types of equations. And I'm going to start with the easiest type of equation with respect to the transcendental types. We're going to start with exponential equations. Logarithmics are sort of like exponentials, so they're not too bad. Trigonometrics are their own animals, so I'm going to break it up into the three different types. I have an exponential equation on the board. It should obviously be an exponential equation because there's an x in the exponent. So that's how you know you're dealing with an exponential equation. This is not an easy one. If this was 9, I bet you guys could play around in your head because 9 can be written as 3 squared. And you can play around with it in your head and figure out, oh, okay, well, I know if this number is going to be like a 3/2 or something like that, then I might be able to get to the right answer. It would actually be a half. All right. But here's what we can do. One of the rules we learned about logarithms is that we can take a logarithm's exponent and write it as a coefficient and vice versa. So if it's not a nice exponential equation, what you might do first is start by doing this. Take a log of both sides. And it could be any log you want. It could be natural log, it could be log base 7, log base 55 pi. It doesn't matter. Obviously, I'm trying to keep it easy, so I'm going to use the common logarithm. All right. What I can do is I can take 2x plus 1, move it to the other side, or as a coefficient. So I'm going to get quantity 2x plus 1 times log 3 is going to be equal to log 7. And now, it's just an easy linear equation. What I'm going to do is, I could either distribute the log 3, because log 3 is just a real number, or I could just divide both sides by log 3. I'm going to do that. Dividing by log 3. So now what I end up with is 2x plus 1 is going to be equal to log 7 over log 3. Now, what a lot of students love to do is they love to go in their calculator and get the approximation for this. I like to mark that wrong because it's not exact anymore. If you're the person that's going to be building bridges or manufacturing cars or rocket ships, I don't want close. I want you to be exact. So I'm going to leave it like this because that's the most exact answer so far. To be able to get the full answer, I'm going to subtract 1 from both sides. So I get 2x equals log 7 divide log 3 minus 1, and then I'm going to divide by 2. So x in its most exact form, log 7 over log 3 minus 1 divided by 2. Okay? If you gave me that answer, that's perfectly fine. Okay? Another way to write the answer using the change of base formula that we saw in the previous section would be to write it as x equals log base 3 of 7. So what we're doing is we're going backwards from the change of base formula. Usually what we do is we take this and we write it as log 7 over log 3. Another way that we can operate is just to go through and make it into the more dense version, or the simplified version. So log base 3 is 7, minus 1 divided by 2. Okay? That would be the exact value. Okay? Don't give me an approximation. Okay? Don't give your boss an approximation unless they ask for it. Give them exact values. Okay? So, if we see an exponential function and it's not a nice base, like 3 and 7, 3 and 15, 3 and 999, which are not powers of 3, then we just introduce a logarithm and we go from there. Okay? All right, let me show you another basic example of this. This one will be even easier. Okay? It's not going to look as easy. Let's say I have something like 3e to, let's say, the 2x squared minus 5 is going to be equal, or let's say minus 18 is going to be equal to negative 12. Now, that looks a lot tougher, but it's not. Okay? here's how I'm going to solve it. I'm going to isolate the term that contains the exponential term, okay, or the exponential expression. So I'm just going to add 18 to both sides, just like I normally would. I get 3e to the 2x squared minus 5 is equal to 6. I'm going to divide both sides by 3. That's easy. Division by 3 yields e to the 2x squared minus 5 equals 2. Now, usually what we would do is introduce a logarithm, okay? But this is a special type. This is the e. E is the natural exponential base. And we talked a little bit about the fact that e and one other function are inverses. Think to yourself for a second. What function is an inverse of natural exponential base? It's the natural logarithmic base, the ln. So what I'm going to do is to get rid of the e, use rule 5 and 6 from the logarithmic section, and we can just take the ln of both sides to get rid of the e. So we're going to get the natural log of e to the 2x squared minus 5 is going to be equal to the natural log of 2. So we still take the log of both sides. This time we're just taking the natural log. I call it the log. Ln of e of something to power just becomes something of power. So we get 2x squared minus 5 equals log 2. From here, now it's just a regular old quadratic type of equations. We don't need a quadratic formula, we just solve it out. I'm going to add 5 to both sides. 1, 2, plus 5. Okay? Now you don't make this 7, because order of operations said you would do ln 2 first. Okay? So it's not ln of 7. You divide by 2. So I get ln 2 plus 5 divided by 2. And then we just take the square root of both sides. To undo the square. And unfortunately, I did something wrong here. Okay? I forgot one thing. Whenever you take the square root, we can't forget that there's a plus and a minus solution. Okay? So we're going to insert our plus and minus every time we take the square root of both sides when solving an equation. Not when we're finding a square root, but when we're solving an equation. Okay. So like I said, this one was a little bit easier, okay? Even though it looked like it was initially a little more difficult, not too bad. Right. Let me show you one more of these exponential types of equations, then we're going to move on to logarithmic types. We've seen examples to where we only have one variable. What if we have two variables? Let's say I have a basic example. 2 to the x equals 5 to the x minus 7. Okay, I want to solve this. Now, of course what we would do is we'd say, okay, well I can't write 2 and 5 as common bases because 5 is not a power of 2, nor is 2 a power of 5, it's nice. So I'm going to introduce a log to both sides, just like we did in the first example. And then I'm going to use that third rule of logarithms, where I can take the exponent and I can move them as coefficients. So I'm going to say x log 2 equals x minus 7 log 5. Now, a lot of students don't like this because now they see an x on both sides and they kind of get confused. Okay? Here's how we take care of it. We're going to get all the x's to one side, everything else to the other side. So I'm going to distribute log 5 to both of the terms. So I get x log 2 equals x log 5 minus 7 log 5. Okay. Then I'm going to move x log 5 to the left-hand side by subtracting. So we get all the x's to one side, just like you usually solve an equation. So I'm going to have x log 2 minus x log 5 is going to be equal to negative 7 log 5. So at least the x's are on one side of the equation. We're only 2 steps away from finishing this, okay? What a lot of students might try to do is think that these are like terms, and they're not. We can't combine them. But what we can do is we can factor out the common x. So I'm going to factor out a common x as the greatest common factor. I'd be left with log 2 minus log 5 equals negative 7 log 5. And then finally, we can divide both sides by log 2 minus log 5. So x could either equal negative 7 log 5 divided by log 2 minus log 5. Another way that we could write this, which is pretty cool, is we could just divide everything by negative 1 or flip all the signs around. So another way to write this, and if you guys get to here, that's fine, but I just want to make sure that you can see like another simplified version. If you multiply the top and the bottom by negative 1, it just flips all the signs around. So I would get positive 7 log 5 divided by log 5 minus log 2. Even cooler, what I could do is I could use that second rule of logarithms, where if I have the same base, and since this is the common logarithm, they both have base 10, I can divide. So I end up with log 5 halves in the denominator. I can also take the 5 and raise it to the 7th power. And then finally, I could use the change of base formula because I have the same bases of 10. So another way that we could write this answer would be log base 5 halves of 5 to the 7th power. And if you really wanted to evaluate 5 to the 7th, you could. I don't know what 5 to the 7th is. Probably something really big that I don't want to. We could take the 7 in front of the log 2. Okay, there's lots of different ways to write this. I just want to make sure that you guys understand that sometimes they use these different rules of logarithms to be able to generate their answers as well. Okay, so this is the algebraic manipulatives necessary to do this. So in the next series, what we're going to do is we're going to take a look at logarithmic equations.